All right. Good morning, good afternoon, everybody. Thank you for joining today's webinar, where we talk about the Ray libraries in practice, how they can be applied for LLM workflows. I'm Michael. I'm on the product team here at Anyscale, and I'm joined by Stephen, field engineer at Anyscale. Stephen will be available throughout this presentation to answer any questions that are posted into chat. So please, as we're going along the presentation, feel free to drop your comments and questions into the chat. Stephen will answer as we go along, and then we'll carve out time at the end to also do kind of live interactive Q&A if there are any questions that you still remain at the end of the session. So just a quick background context. We're going to talk about the Ray libraries, but I just want to quickly introduce Ray. So Ray is a distributed execution engine for scaling Python workloads. So the founders of Anyscale and the inventors of the Ray framework were doing their PhD at UC Berkeley in AI research, and they found that they were spending more of their time wrestling with distributed systems issues than actually doing AI research. And a lot of the other distributed computing frameworks at the time did not really solve a lot of the challenges that they were facing in AI research. And so this is why they invented Ray to kind of solve for some of those problems in distributed computing. And fast forward to today, Ray is kind of becoming the emerging standard for distributed computing across digital native and enterprise companies. We see more than 1 million Ray clusters launched per week globally. The Ray project has had over 1,000 contributors, and it's been widely adopted by some of the most iconic and interesting companies that exist today. So today, we're going to talk about the Ray libraries and why they exist to kind of simplify the developer experience around using Ray and getting developers productive on Ray much more quickly. We'll frame this all through the context of a named entity recognition task where we fine-tune a model with Ray train for named entity recognition. We use Ray data for doing large-scale evaluations and batch inference on for that task. And then we deploy the fine-tuned model with Ray serve for online inference. So I'll kind of give a background on what we're going to show and how the libraries help to accomplish those use cases. And then we'll do a live demo of actually doing this process. And then we'll kind of recap and open the floor for Q&A. So why do the Ray libraries exist in the first place? Well, Ray under the hood, or Ray kind of the core framework is very powerful, right? You can take any bit of existing Python code, add a simple Ray remote decorator, and now that code can run in a distributed environment. You just need to change a little bit about how you materialize objects, and everything kind of just works distributed. But sometimes for common use cases, especially in the AI and ML space, the patterns that people are using for Ray are pretty similar, and this low-level control is not necessarily what you need. And also, some of the concepts can kind of be a little bit unfamiliar to for ML developers who are not distributed systems experts. And so for these kind of repeat use cases, low-level control is not always what you want. And the Ray libraries exist to give a higher level of abstraction on top of Ray to really accelerate the developer productivity for building applications in the ML and AI space. So these libraries kind of are Pythonic in nature, and so they integrate very, very well with the existing ML ecosystem and the tools that ML developers know and love. So for example, uh, if you're using PyTorch for training, right, you don't have to learn a new framework to leverage the distributed capabilities of Ray. You can just write your PyTorch code and interoperate with Ray train, and now your training code can run in a distributed environment. And this is kind of powerful because it helps developers get productive very quickly. And when they're ready to scale out their workloads, given that the libraries are built around Ray, and Ray is battle tested by some of the largest enterprise, we know that this workload is going to scale up very effectively. And within each library, there's also kind of optimizations that are workload aware. So for like Ray data, for instance, we'll go into more detail about the architecture, but the streaming execution pattern of Ray data is like really good for large scale data processing. So when we talk about the Ray libraries, all of them are powered by Ray, but let's talk about kind of what they're each oriented for. So Ray Train is a library for distributed training. Ray Data is for large scale data set processing. Ray Tune is a library for hyperparameter optimization. Ray Serve is a library for large scale API serving and model serving. And RLib is our library for reinforcement learning. And all of these five libraries are powered by Ray under the hood. They employ kind of the primitives that exist in Ray around tasks and actors and placement groups and use a distributed object store uh, to power the scale out and distributed capabilities. So in today's example, we're going to talk about three libraries: Ray Train, Ray Data, and Ray Serve. And we'll talk about them in the context of building a named entity recognition system. And so what is named entity recognition? Very simply, it's kind of a technique for extracting categorical and structured data from unstructured text. So in this kind of notional example here, for a capstone project at Harvard University, the named entity recognition process is able to extract and kind of find that Harvard University's Institute of Applied Computational Science and the IEEE are organizations contained in this text, that natural language processing and named entity recognition are methods, and Spacey, BERT, PyTorch, and Redshifts are all products that are used. And uh, Named entity recognition is not something that's new. It's kind of a subclass of problems in the NLP space, and has been around for a long time. But with kind of the advent of generative AI and large language models, uh, the techniques that are used to perform NER have kind of evolved over time. And today, large language models and generative AI are very effective at doing these sorts of tasks. In our demonstration, we're going to do a fine tuning on the Vigo data set for meaning representation. This is a data set that's available from Hugging Face and contains labeled pairs of raw text and meaning representations for reviews of game publishers and video games. And you might say, okay, so like what's the actual like use case here? Like, why do I care about named entity representation in this context? So let's say I'm one of these video game publishers, and maybe I have many titles, and there are hundreds of thousands or even millions of reviews for for these video games out there, and I want to do some sort of analysis on those reviews. It's really hard to just process that text at scale and really like glean any meaningful analytics from it. So performing this meaning representation, this named entity recognition task on the unstructured data set to give it some structure helps to make those sorts of analyses possible. And you can think about, that in two forms. Like maybe I want to do a one-off analysis of all of the reviews that have ever been given for my portfolio of games. That's kind of more of a like large scale. I need to go do this extraction across a very large corpus of text data. But maybe you also want to do this capability in real time for new reviews as they come in, so that you can, for instance, prioritize positive reviews to show up on the first page of like where these reviews are left. So kind of two flavors: offline processing for named entity recognition and online processing. And so how does that all fit into the context of what we're going to show today? We're going to show an end-to-end LLM workflow for named entity recognition on Anyscale. So from the data processing side, we'll actually start just with this curated Vigo data set available from Hugging Face. I want to note here that in a production or real world scenario, Ray data is actually a great fit for doing the pre-processing that's required to curate the data set at very large scale. We're not going to use Ray data for this purpose in today's webinar, just to accelerate the demonstration. We're going to use a previously curated data set. For the training, we're going to use Ray Train to plus Llama Factory to do the LoRa fine tuning of one of the 7 billion parameter Quen models. And so for those that aren't familiar with Llama Factory, it's a great open source library that makes it really, really easy to do the fine tuning. However, Llama Factory out of the box doesn't have any capability for distributed fine tuning. So there is a first class integration with Ray Train that allows Llama Factory fine tuning to happen in a multi-node, multi-GPU setup, and that will accelerate the fine tuning process itself. And in the demo that we'll see, I actually don't have to write any Ray Train code explicitly because of this first party integration that Llama Factory has with Ray Train. All I do is define my scaling configuration in a YAML file as part of the fine-tuning setup, and all of the scaling and distribution of the work happens under the hood. So really, really easy API, and we'll go into more detail there. And then for inference, we kind of talked about the two patterns of inference: offline batch inference for large-scale data sets. We'll use Ray Data plus VLLM to do this. And then for the online inference, we'll use Ray Serve with VLLM and kind of deploy a production-ready model and with an OpenAI compatible endpoint out for scalable serving for online applications. So let's go into a little bit more detail about each of these libraries that we're going to use to accomplish the task before we get into the demo. So Ray Train, though in today's demo we're going to use it primarily for fine tuning, it's really a library that can use for any sort of distributed training task, whether that's pre-training language models or training classical ML models, etc. And Ray Train is really great for ML developers who know and love the tools that they use, like XGBoost or PyTorch for model training, but want to accelerate their workflows and more effectively utilize the hardware resources that are available to them within their organization. And so like kind of the cool part about Ray Train is its interoperability with the rest of the Python and ML ecosystem and the simple API, right? You just define your scaling config and you write your normal PyTorch code, and Ray Train figures out how to deliver to distribute the training process across the nodes that you specify in your scaling config. And as soon as you start to think about problems in a distributed context, it's you get a lot more complexity around like, how do I do debugging and how do I observe the state of the system? How do I handle fault tolerance when there are more nodes at play? So Ray Data has a lot of the observability, fault tolerance, and checkpointing capabilities out of the box to make it a lot easier to move from a single node setup to a distributed setup. And lastly, we won't really see this in today's demo, but one of the major benefits of Ray Train and of the Ray ecosystem more generally is kind of the interoperability between the different libraries. So Ray Train is really, you can really effectively use it with Ray Data for trainer loading for very large scale data sets. The APIs exist to make that process like super easy. So if we look a little bit deeper at the API for Ray Train, as you can see kind of on the left, you're just writing your training function in whatever library that is most useful for you, whether it's PyTorch or XGBoost, etc. And the code that you write is actually pretty much the same. And Ray just kind of figures out how to distribute that code across a distributed environment. You just define your scaling config, and Ray knows how to interpret that to distribute the fine tune or the training activity. And so in this kind of example, right, the number of workers is set to 4. We're using GPUs for the training, but Ray is super, like, it's ready to scale up to a much larger workload, and using the accelerator hardware that is kind of most applicable for the task at hand, right? Different training workloads have different requirements of resources and So you can think like very different if you're fine-tuning a large language model versus if you're, pre-training something like a, 70 billion parameter model. You're going to have very different workload specifications, and ray train gives you kind of the level of control and granularity to optimize for resource utilization. And in today's example, this is kind of exactly the process that we're going to follow. As I mentioned, the integration with Llama Factory makes everything a lot easier. Actually, I don't even have to write any ray train code. I just specify in the config file how I want to distribute the fine tuning exercise, and ray train under the hood does the execution. All right, let's move on to ray data. So ray data again is the library that we're going to use to do large scale evaluations of our fine-tuned model, and it's super optimized for this batch inference task, and we'll go into a little detail about why that is. So what is ray data? It's a data processing engine built for AI workloads, and a lot of the existing data processing frameworks out there are not quite as well positioned as Ray Data for these AI workloads. And that's primarily because Ray Data has great support for dealing with multimodal data types, which are becoming increasingly more prevalent in AI workloads. And given that it's powered by Ray under the hood, there's a robust and kind of granular support for accelerators at various stages of a data pipeline. We'll go into a little bit more detail on the API in the next slide. But if you think about like a data processing pipeline as like a sequential stepwise function of stateful operations, Ray data kind of gives you the unique ability to specify granular hardware requirements at each stage of data processing. And like the rest of the Ray like the rest of the Ray libraries and the Ray ecosystem more generally, it interoperates really well with the tools that you already know and use in your day-to-day workflow. Looking at the API, if you look at this kind of notional data pipeline, reading, pre-processing, transforming through some deep learning model, post-processing, and then writing to cloud storage, like this is kind of a pretty common data pipeline that we see with Ray data. You see these kind of map functions and these map batches functions that are written in the API. This is a way to do kind of custom user-defined stateful transformations sequentially on like through the streaming execution of the data set as it's processed. And so why this is super powerful because it means that, in your pre-processing, which might be CPU intensive, you can specify exactly the hardware resources that need to be used to accomplish the pre-processing, and then batch by batch, block by block, you can then pass and stream the data to the GPU to do maybe some deep learning transformation. Maybe it's like you have a large text data set that you need to pre-process, and then you need to run it through an embedder to compute embeddings. You can really optimize that end-to-end pipeline for cost because of the ability to mix heterogeneous hardware at different steps of the data set processing. And another kind of interesting and notable thing about Ray data, it's lazily executed and executed in batches in a streaming fashion. So this first command where I define the pipeline, that actually doesn't execute the data set. This just creates the execution plan. It's not until there's some materialization API that gets triggered, like writing to a Parquet file, where the pipeline actually will be executed and data will actually be materialized. And this means kind of that like you can define your pipelines, and not until the pipeline is ready to execute do you need to marshal and schedule the resources required to run that pipeline end to end. And the batching and the streaming helps to take some of the resource pressure off to avoid things like out of memory with large data sets and et cetera. And so in today's demo, we're actually going to use the Ray Data LLM library, which sits at a slightly higher level of abstraction than even what I was just showing, highly optimized for text-based LLM processing. with kind of some intelligent back pressuring at different stages of the inference pipeline, because some of the pre-processing and post-processing is actually CPU bound, whereas the generation of the tokens, the inference task with the model is GPU bound. And so throughout this pipeline, there's like very intelligent kind of optimizate workload aware optimizations to generate lots of text very quickly. And so in our data set, right, it's a set of video game reviews. We're prompting a language model to do the meaning representation, and then we're outputting the meaning representation that is inferred by the fine-tuned model. So lastly, we'll talk about RayServe. And again, RayServe is a framework for deploying and serving reliable and scalable online applications. And RayServe is really, really useful because, again, of the interoperability benefits that you get with the Ray and Python ecosystem more generally. It gives you, through a single deployment, the ability to mix and match both business logic and models. So other kind of model deployment frameworks are kind of more tensor in, tensor out. And what this means is that you have a much more complex microservices backend with lots of microservice, some handling the business logic, some handling the model inference. And that leads to a lot of complexities. RayServe allows you to couple these things together, which is an opportunity to significantly simplify the microservices backend that you might have to otherwise support and maintain. And in a similar vein, the RayServe API has a first-class support for kind of chaining multiple models and business logic together through like a DAG. And this is really cool because it's like a very simple API for doing this blending of business logic and multiple models. But the real power here is that you still maintain control over each step of the DAG in terms of resource allocation. So you can scale independently different nodes in the graph. And so what this means is that this is especially important for, like, as agentic AI becomes a really significant thing that is being adopted by the enterprise. Scaling these agentic backends is going to be really tricky, and applications like or frameworks like RayServe makes it really easy to performantly build and scale these agentic applications. So with that, in the demo today, it's gonna be a much more kind of trivial just deployment of an ML, of the fine-tuned model through a RayServe application and deployed as an Anyscale service. The API for RayServe kind of has two angles. It serves developers for fast experimentation and developer productivity, where you can just kind of annotate your serve deployment for a model and really like easily deploy that for inference and kind of rapidly prototype. But the same API is also accessible through kind of a config-based framework, which is much more suited for enterprise and production use cases, where operators and platform engineers are much used to deploying and managing deployments through config. And within RayServe, you define your kind of scaling parameters for the model for the replica, and that replica could be for an API, or it could be for a model, or it could just be for any Python application. So generally, the use case that we see most prevalent is deployment of models and LLMs and the chaining of the systems together. But RayServe is also really great for serving APIs and other applications. And we'll deploy our RayServe application on Anyscale. The whole demonstration that I'm going to do is going to be with Anyscale, which gives some nice kind of additional capabilities around how you can have production-ready deployments of RayServe applications, kind of just out of the box with no additional configuration. And so we're about to jump into the demo, but first I just want to introduce Anyscale, which is kind of the enterprise platform for building, running, and scaling Ray applications. It gives a great developer experience for for building these Ray applications, and then all of the supporting infrastructure that's required to get your Ray applications to production. And there are three kind of primary uh, interfaces within Anyscale. Anyscale workspaces, which are Ray clusters for interactive development. So the target persona here is the ML developer who needs to experiment and then eventually scale out their application that they're building with Ray or the Ray libraries. Then there are Anyscale jobs, which are once I've developed my application and I need a durable and production grade environment to run those applications at scale. Anyscale jobs are most well suited for this. And kind of the difference between Anyscale jobs are great because one, the resources that they consume are ephemeral. So the Ray cluster is created for the job and then destroyed after the job. We also have concept of job queues for kind of like high frequency reuse of existing resources. But generally the pattern that we follow is deploying Anyscale jobs into ephemeral clusters. And the jobs also have kind of retry logic and failure handling built in out of the box. So very good for these production workloads. And lastly, we have Anyscale services, which are long-living Ray clusters for online applications. And this is kind of how we'll deploy our fine-tuned language model today. And they're ready, they're enterprise and production ready, right, with high availability and failure handling and fault tolerance out of the box. And also kind of the ability to do blue-green rolling deployments, upgrades, downgrades, etc. So that I just leave it high level. We'll show the Anyscale developer experience along the way in the demo. But with that, let me jump into the demo. So here I am in my Anyscale workspace, and I'm going to walk through a notebook for how we fine-tune this entity recognition model based off the Quen model. Just really quick, I'm kind of in this managed VS Code remote development experience. I also could switch to a Jupyter experience. I have a direct access to a terminal, but we also have kind of desktop integrations through where you can open in cursor. That's my favorite way to develop Ray applications generally. And it would be through my desktop cursor application. I SSH into the Ray cluster that I'm developing into, and it's really just like this pretty seamless, magical development experience where my changes are being synced constantly back into this remote development environment. I'll show the VS Code experience, the managed experience for today's demo. And what I'm going to do is kind of go through and run a couple of cells in this notebook just so that we kick off the fine-tuning process, which will take, a few minutes to complete. And after I do that, then I'll walk through and explain everything that I'm doing. And okay, so that should kick off the fine-tuning. So before I kind of walk through what I just did, let me just give a quick overview of the Anyscale workspace that I'm in. So this is my workspace name. It's kind of was automatically created for me. It has information about the container that I'm using, which has all of the dependencies that I need that are baked right into the image. And it also has what is called a compute configuration, which specifies the hardware resources that are available to me in at development time. And I can change these by adding additional worker groups. So if I needed an A100 GPU, for instance, I can add these instances as needed. Right now, I have configured my environment up front to have 4 L4 GPUs already kind of there and ready for me to use. Again, I could have set this for auto scaling, set this to 0, had it auto scale only when I kicked off that fine tuning job. For the purpose of this demo, I'm actually not doing that because just to save a little bit of the instant start time. But generally, for these GPU resources, if you're getting them on demand, you're sometimes bound by what the cloud provider has available. So it's safer for the demo just for me to have this like pre-provisioned and ready to go. But in a real production scenario, or if you're trying to save costs, you would set this to auto scale to 0, and Ray can very, very quickly and efficiently scale up nodes. We've to up to thousands of nodes in like less in just a few minutes, faster than many other distributed systems. Um, Let me I also just back in my VS Code, I will kind of walk through the code that I just ran and kind of what's going on right now under the hood. And so uh, the first thing that I did was install dependencies, right? So we have some of the dependencies like Ray baked into the container image that is deployed for this workspace. But I also needed a couple of other dependencies to actually build the application, including Llama Factory and TensorBoard if I want to look into the status of my fine-tuning job. And this is kind of Anyscale has some really great uh, dependency management capabilities where I could run this pip install command just to install this, and showing these dependencies now show up in my UI. And what this means that these dependencies are all registered and will be propagated to the worker nodes that are actually running the Ray application. This solves for a major pain point of working with Ray more generally, where you're kind of finding yourself spinning up and adding nodes to your worker nodes to your compute config, and dependencies sometimes are not available if you're working just with the open source Ray project. Anyscale makes this dependency management process like very seamless. So I also did the data ingestion, right? So basically just cleaning up the old data set and then downloading the data set from an S3 bucket and moving it into shared storage that's accessible from not just the head node of my cluster, which I'm working in right now, but also from the worker nodes that are going to have to read the data as well. So looking at the first row of this data set, it's we showed kind of in the slides, but just proving that this is actually what we're doing, right? We have an instruction uh, that we're using as the fine-tuning instruction. We have the input, and then we have the output. The input being the free text, the output being the structured text. And this is kind of the prompt that we're using for the fine-tuning. This is just kind of metadata about the data set. And we went through kind of the architecture, and so this is interesting and worth clicking on really quickly. This is the config file that Llama Factory uses to understand the specifications for how the fine tuning should be run. And so we have all these different kind of parameters that are set around like the type of fine tuning that we're doing, information about the data set that we're fine tuning on, where to store the outputs, and then we also have kind of the Ray configuration. As I mentioned, there's a first class integration between Llama Factory and Ray train, where in config as part of my normal Llama Factory process, I can just specify, the number of workers that I want to use, the types of accelerator hardware that I want to use. In this case, we're doing the fine tuning with a 4x L4 node, and how I want to actually place the Ray actors under the hood to optimize for fast execution of the distributed chaining activity. And so this makes it just really easy now to take a tool, Llama Factory, that's easy to use and make it work in a distributed environment. I also specify these kind of hyperparameters for the fine tuning process and my eval parameters for how I want to go through and do the evaluation. And this is just showing that it's one of the Quen, the 2.57b instruct model. This is a 7 billion parameter model that we're fine tuning. So not a small language model, not the largest language model. And finally, I just ran the code for the fine tuning to initiate the fine tuning job with this Llama Factory CLI. And you can see that this has been running for 6 minutes now. The logs are all kind of outputted to the Jupyter console here. But these logs are also written in kind of the unified log viewer that we have with available from Anyscale. And so we can see this information now is being written here, and that was at, last log was at 10:37, which is, the same time that it is now. And this allows me, from an applications perspective, to understand where I am throughout the fine-tuning process. We also can see here workspace events for the Anyscale workspace that I'm in. There have been no workspace events in the last hour, but things that you might see here, if I change it to last 3 hours, you can say I started this workspace at 9 o'clock, and it tells me information about the instances that were launched. I was talking about how earlier about how the cloud provider sometimes can if you're scaling up on-demand instances, it can take some time. Anyscale handles all of the retry logic until eventually it's able to get a node and schedule it. Now, Anyscale also allows you to, if you have GPU reservations, to connect to those reservations so that you can ensure that you have infrastructure ready on demand whenever you need it. But so this is kind of like the log viewer. I can also see cluster level metrics. This is just for the last 5 minutes, but if I change it to the last 30 minutes, you can see that when I kicked off that fine tuning job, shortly thereafter, our hardware utilization for our GPUs and our memory utilization for our GPUs jumped to nearly 100%. And actually, you can see now that the compute resources are inactive. That means my fine-tuning job has completed, and we should see these kind of node metrics come down back to zero. Really quick, one more point that I want to make. We also have kind of workload-specific dashboards that exist in Anyscale beyond just what you get with open source array that really helps to contextualize what is going on throughout the training process. So we have logs for each actor that's used in the distributed training, and you can do things like see the CPU flame graph to profile the actual training activity and understand and better debug where there might be bottlenecks and where you might be running into issues. Now, we also have the open source Ray dashboard available right from here. For those who are familiar with Ray, this is the same dashboard that you get with open source that gives kind of full observability into what's happening within your Ray cluster. All right, so with that, I can see that I made it to 100% with my fine tuning job. I have kind of some high level stats about this. I also have a tensor board running for this training activity. It's not that interesting because we're only running one single iteration for 4 epochs. In a production scenario, like the integration with TensorBoard and other tools like weights and biases is kind of what you want for the training level observability on top of everything that's going on in the Ray distributed system under the hood. But I don't need to show that, I think, for this activity. So now let's run a couple more cells. This is just kind of showing that we the training loss. We walked through kind of this observability experience, and now I'm going to save the model weights to artifact storage. So this is cluster storage that's accessible across Anyscale. And this is important because I wanted to eventually deploy this model to an Anyscale service, and so we'll do that shortly. But this is kind of just now copying the model weights so that they're available and confirming that the model weights are available from this mount path in cluster storage. And then I can run all of the rest of these. And now we're ready to kind of, now that this model is available centrally, we can use this model for batch inference. So really quickly, we kind of already went through how we use Ray data to do the batch inference process, but I just want to double click now on the code that we're writing to do the batch inference process, right? Like this is a very simple config-based API to do something extremely powerful, which is iterate across a data set and do large scale text generation with a large language model using VLM as the inference engine under the hood. And so I go and I define that config. In this config, we're defining things like the pipeline parallel size and the tensor parallel size and enabling chunked prefill and prefix caching for performance. And so now I'm going to run this processor API, which contains my prompt and the row of data that we're iterating across, specifying some of the engine keyword arguments for the temperature and the max tokens, and then specifying a post-processing function for actually doing the grabbing the output from the API payload. And so, as I mentioned earlier, since Ray data is all like lazily executed, these first kind of two commands here that I'm about to run will not actually execute the data set. It's the the third command that actually materializes the data set and starts the execution of the data set. And so, as we're kind of reusing the same L4 hardware for the inference, and we're actually scheduling CPUs for each stateful actor for the pre-processing and the post-processing, which are not GPU bound. And so, what is this actually doing now? So this is deploying the model through VLLM, the fine-tuned model that we just created, and doing like basically the initialization of the engine, and then it will send this large set of input data in batches through the model, super efficiently, generating the output. And so as this starts to happen, so you can see the logs here. I could also show you these logs from the unified logs viewer, but I'm going to keep it in the workspace. And so we can see here that we're now in the token generation part, which is really it is the longest step, but we're getting insanely good prompt throughput because of the optimizations that exist within Ray data. So we're getting 7,000 tokens per second on the prompts, and like almost 1,000 tokens per second on the generation throughput. So this is like super efficient. We're able to spin through this set of 1,000 input prompts in like 36 seconds, and now this is complete, and just kind of showing that this is the first. We took one from the data set, which is like materialized that first output, and we can see that the output that's here is it's kind of extracted the meaning representation here. And so now, if we want to understand how did we do with our fine-tuned model, so you saw that in my last run we achieved 59% accuracy. In this one, we achieved 60.1% accuracy. Again, the purpose here is not to build the best model possible. That would take several more iterations and several more epochs for training. But just to keep a quick and tight demonstration of the capabilities, we are able to just very quickly get a model that correctly, based off our labeled data set, gets 60% accuracy on like the task it was fine-tuned for. All right, so that's kind of the batch inference and how Ray data helps to accelerate there. Now I'm going to finally show how we would serve that fine-tuned model for online inference with RayServe. And just really quick, before I move on there, I also want to show the dataset observability feature that we have in Anyscale. This is kind of the batch inference process that I just ran on a dataset execution. You can see that it ran each of these steps across the 1,000 rows of data. There's some really cool views in here for like to help with debugging. I can actually visually see the different steps in the DAG for how the pipeline is composed, and I can see integrated like logs that are contextual logs, just showing the execution of this data set, and really help facilitate the debugging process for this feature. All right, so back to RayServe. So I have this LLM config that I've defined here, and most important here is kind of showing how we are planning for this online service RayServe application to scale up and down. And so it's also using VLLM under the hood, but VLLM is really only an engine for single replica. RayServe is what allows BLM to scale up to multiple replicas. And there's some really smart optimizations built into RayServe to help scale out and improve performance. And so I'm going to run this, set the config, and then this is all it takes to now deploy my RayServe application into my workspace. So I'm not running this as an Anyscale service just yet. I'm deploying just for quick prototyping into my Anyscale workspace and standing up the serve backend for that I can then exposing an endpoint for online inference. And if I show quickly in the open source RayServe dashboard, it hasn't come up yet, but at some point, once the serve application has started, you'll start to see this dashboard be populated with like the metrics for RayServe. And so again, it's a similar. Always when you're deploying a model to VLLM, there's like some initialization process that needs to happen for the engine. But once this model is deployed, then I can use it interactively the same way that I might use a hosted endpoint from an LLM service provider. I'll show this here in a second, but this like basically allows me to stream tokens from the deployment. And finally, after I'll show that in 1 second. But let's say I want to now I'm happy with my fine tuning job and I actually want to submit that as an Anyscale job. Now that's as simple as running this Anyscale job submit command, which like takes the compute config and container state of my environment and replicates it into an Anyscale job. And so the more common practice here is through, I would push my code to some source control, and there would be some CI process on the back end that would then schedule and orchestrate these jobs in the production ready jobs infrastructure, and that kind of blends together the nice CI/CD process and and safety that enterprise need with the durable backend infrastructure for jobs. But it's as simple as running the CLI job to kick off the fine tuning as an Anyscale job, and I'll show how this kind of now in my jobs UI, I can see that I've kicked off this fine-tuned Quen for named entity recognition. The cluster is now being created, and that'll run for 6 minutes or whatever. We won't need to show that. But now that the Anyscale service is deployed and running in my workspace, now I can interact with that service the same way that I would kind of any sort of hosted model endpoint. And so you can see here, it's like printing out the tokens, streaming the tokens in real time. Now, I would, similar to how I just kind of deployed the job for production, now I can do the same thing, deploy my LLM as an Anyscale service, just with this simple API and this simple config file that I've defined here, the serve config, which specifies the deployment, and then the model config, which configures the auto scaling and the parameters and the engine keywords for the model. And so I just run this, and now this is kind of updating an existing service that I have, and similar to the UI for jobs, I have this UI for services, and I had previously deployed this LLM here to the service. Now I know that the service is upgrading and doing a canary deployment of my previous of this fine-tuned model. 100% of the traffic is being routed to the primary version. The canary version, 0% is being routed to it. And what this means is that you can deploy Anyscale services incrementally without needing to double the resources required. So replica by replica, the model is being updated. All right, that's it for the demo. Let's just quickly recap what we did, and I want to make sure I leave enough time with 8 minutes at the end for demonstration. So what did we do? We pulled the data set, or sorry, leave a few minutes at the end for Q&A. What did we do in this demo? We read the curated data set from Hugging Face. We fine-tuned the Quen model in about 5 to 10 minutes on 4 L4 GPUs using ray train. We did a small-scale LLM evaluation for 1,000 rows of data using ray data, and performed batch inference across each of those rows of data. And we deployed our model as a production endpoint, exposing an OpenAI compatible API for scalable inference using RayServe with auto-scaling enabled to handle variable throughput cost efficiently. And as we kind of discussed, RayTrain really simplified the distributed fine-tuning process. Ray data offered great performance for large-scale batch inference because of a lot of the workload-aware optimizations that exist within Ray data. And RayServe made it easy and cost-effective for us to serve this LLM at scale, where model replicas will scale up and down depending on traffic. And one thing that we didn't at all discuss is the Anyscale Ray engine under the hood, which is called Ray Turbo. And this is kind of a proprietary optimized version of Ray that offers higher performance, lower costs, better reliability, better scalability for all of these kind of most common AI workloads. So with that, thank you so much for joining today's webinar, and I hope this was a good use of your time and you learned something interesting. Please, if you're interested in anything that you saw, reach out to our team. We can give you free credits with Anyscale. You can actually go and download and connect to the demo that I showed today and run it yourself on your own infrastructure. The repo will be shared at the end of the session. But please also reach out to our team if you have any questions or if you need training. And lastly, the Ray community is very vibrant, and there's a lot of super engaged developers and platform people out there. Please join if you're not already a part of our community. And it's a great place to learn something and get involved with the Ray project. So with that, I will turn it over to Stephen for answering questions. Apologies for just to have 5 minutes here for questions, but I hope we can have a meaningful conversation.
Thank you, Michael. Yes, I know there's quite a few questions we've had in the chat so far. I think some of the biggest questions we have are, what is the difference between ray train and if you used another library like torch distributed or deep speed? I'll say that ray train does not replace deep speed. Instead, what we do is we created powerful integrations with the entire ecosystem of the different training frameworks. And this gives you not only like, you don't have to migrate the code in a large way. It's usually a few lines of code's difference, but then it also gives you better scalability, better fault tolerance, better observability, as well as having more pre-processing ability because you can now integrate Ray data instead of just using your standard PyTorch data loader. Now you can start doing more complicated like ETL style transformations or map functions that make it easier to put everything in the same pipeline. The other one I'm seeing that's very popular, a question is like when we deploy this on Kubernetes. So on open source Ray, Kubernetes is one of the most popular ways to deploy Ray. So it's very like different parts of like how to distribute the application. So Kubernetes, like this is where you'd be managing the infrastructure through the pods of the cluster, but then it's not actually distributing out the individual threads. This is where Ray comes in to make it very Pythonic and very easy to use for distributing the application itself on top of Kubernetes. So I normally see a lot of open source Ray clusters use Kubernetes. And that's usually what I would advise. For when you are looking at Anyscale, which is advantages over it, or you get Ray Turbo as well as the better infrastructure and the professional support and expertise, we can deploy it on top of directive VMs, which this is very, very quick. This can be auto scaling for like hundreds, if not 1,000 nodes in under a minute. You know, cold start from EC2, so directive VM stacks. It also works with other directive VM for on-premise solutions. But also if you have existing Kubernetes stacks, then we're able to deploy on that pretty seamlessly through the Anyscale operator. Are there any other major questions we should answer in the couple minutes we have left?
Your call, Stephen. I think I'm leaving the slide up, so I can't see the questions.
I think the main question is like, is the presentation demo code available to like be shared?
Yes, yeah. So all of the demo code is available in the open source, and we will make sure to share the demo code in the follow-up email. And the demo code is like very well uh, kind of documented, and highly optimized for use on any scale. So please also, if you're interested in these free credits, we're happy to make them available to you to walk through the demo flow. Any
And
other
then,
any
oh,
other
I think,
questions?
yeah, I'm just looking over some of the answer questions too. Um, See if there's some common threads we should discuss. Uh, but then again, please feel free. I'm going to put my name. I put my name in some of the and email in the chats, but please feel free to reach out over LinkedIn or on the open source Ray Slack for any further questions. We're happy to answer them. If there's any, there was also a few bugs people were reporting. If you come across any bugs with using Ray, please put them into the GitHub Ray um, issues, and our team will work on them as soon as we can.
Yeah, echo that. And thank you all for the time and attention today. So we will for any questions that were unanswered, we will make sure to follow up on them in the as action items after the webinar. And yeah, echo Stephen. Anytime you have any issues, please don't hesitate to reach out to the Ray team. Um, we're here to help. All right, thank you all for joining.
Yep. Thank you, everyone.